Hi everyone, we are team number 10, London Aquatic Center. Let's begin. This week we present you the exterior construction of the Aquatic Center. These are the contents, starting with the review. The exterior structure and calculation will follow next. Let's start it with the review. The Aquatic Center could not be connected to the site-wide non-potable water network due to insufficient space in the surface corridor connecting the venue to the main site. Alternatively, it employs a 53,000 greywater recycling system to exploit the vast quantities of wastewater. Approximately one-third of this processed water, 67.5 megaliters, is treated to a non-potable standard to meet toilet and urinal flushing demand, substituting mains water use. The Aquatics Center also employs an innovative solution to reduce energy consumption during games time operation. Detailed thermal modeling and elemental redesign of the 15,000 seat temporary structures enable mechanical cooling to be entirely eliminated. The resulting carbon saving during games time operation is approximately 56 tons and the resultant cost saving over 250,000 pounds. This tent solution meant that fewer tons of china clay waste were deposited, and fewer tons of primary aggregates were carried. Starting with tent solution, construction team tried to use secondary materials for the construction. Next, we present about GGBS cement. It is strong, high durability, and good appearance. This furnace-like is highly symmetrical and high in calcium silicate hydrate, which is strength-enhancing compound, increase the strength, durability, and appearance of the concrete. Over 150,000 tons of concrete was used in the Aquatic Center. The sustainability of the center can be demonstrated by over 4,000 tons of embodied CO2 savings and substitution of over 29,000 tons of primary aggregate. Let's talk about roof structure. There are several layers created in the top of the roof. Sheeting and waterproofing were put down over the steel supports. Mechanical systems were placed into the space. Spaces were added before the final aluminum sheeting was added. The process of rolling out the sheeting for the roof only took a team of 25. It took only a month to cover the roof fully with the last aluminum finish. The connection between the roof and the support columns were the sliding joint. Joints like these are commonly found in bridges. The joint can slide up to 2 feet. This is to allow for expansion and contraction that occurs in the steel roof structure due to temperature changes. As you can see in this picture, roof structure is made of 3 parts and supports. First, the upper roof layer consists of robust aluminum, half of which is recycled. Next, the steel bones are a combination of shaped trusses to get a double curve, allowing a column-free clear view of the pools. It weighs 3,000 tons, and the hardwood ceiling is made up of 37,000 individual strips. The complete structure of 11,000 square meters is supported only in 3 points: a concrete wall at the south end and 2 concrete cores at the north side. Some of the steel trusses of the roof are 40 meters long and weigh 20 tons. Spanning from north to south, they cover the generously sized main area without any in-between supports. Just 2 slim concrete supports and a concrete wall located opposite these at southern end suffice to conduct the force of the hidden steel space framework construction into the ground. As much as 2,800 tons of steel were needed to give the 160-meter long and 80-meter wide roof its light and floating look. This steel framework was initially constructed on temporary supports before the entire 3,000-ton structure was lifted up in a single movement and successfully placed back down onto its permanent concrete supports. The Venus roof proved to be one of the most complex engineering challenges of the Olympic Park's big structures. A series of long-span trusses from the roof, they were erected in a fan arrangement to create the plane geometry of the structure. The middle truss has a span of approximately 120 meters to a primary truss, which in turn spans 54 meters in a transverse direction between two concrete cores. These center fan trusses cantilever beyond the primary truss to form a 30-meter overhanging canopy at the northern end. And this is the video that explains roof construction process. And from now on, let's analyze how roof part be solid without collapsing. The roof structure comprises a series of long span trusses spanning the length of the main pool hole. From the transverse truss mounted on a southern retaining wall bearings to another transverse truss spanning between the northern concrete cores. The main trusses lie in a fan arrangement to create the plane shape of the roof. The center fan trusses cantilever northwards beyond the north transverse truss 100 feet to form an overhanging canopy over the main public entrance plaza. The center fan trusses carry load in truss sections spanning between the north and south transverse trusses, which carry the load down to the supporting bearings on the concrete structure below. Under uniform loading, the two opposite inclined arches in the wing areas balance each other, forming a compression hoop around the roof perimeter. A tension force arises from the changing in geometry of the compression hoop in plan at the kinks, which occur at the wingtips, and this is resisted by a tension tie across the center, and the resulting tension force occur in the central fan trusses. The structure of the roof can be deduced to a dome form. In a dome structure, at the angle 34 degrees to the normal that separates compression and tensile forces. In the London Aquatic Centre, the angle of the roof is 30 degrees. Therefore, it creates a compression hoop instead of tension ring if the angle was greater than 34 degrees. The attraction of this building is on the roof, and it has an unusual shape on the outside. The 118,400 feet square structure spans a column-free area 530 feet long and up to 300 feet wide, and it is supported on bearings on two concrete cores. The roof contains about 3,200 tons of structural steel, of which 2,000 tons are fabricated plate girders with a structure connection totaling around 600 tons. It comprises a series of long span members, so it will be vulnerable to the bending moment by roof's weight. We should calculate and analyze whether it could adversely affect the building. As we assume that the total weight is W pound per feet, we can get the reaction force AY at northern support core and BY at southern retaining wall. After replacing the distributed load with the concentrated load, we can set up some equations to obtain the values of the reaction flow AY and BY. Reaction force values and bending moment values were obtained by several equations. And we can get shear force diagrams and bending moment diagram. As we can see in this graph, we can see that bending moment has high value compared to reaction forces. For that reason, they use this series of trusses because its simplicity belies its exceptional ability to span very large distance with great efficiency. It's efficiency that makes them well suited as this building's roof. And this roof is exposed to a pure gravity load as well as the covered roof, so we should evaluate the stress and deflection fields to see if it can sustain those weights. Changing any of the pressed truss bridges dimensions or materials affect its ability to handle loads. That's one of the reasons why it has the inclined arch shape like this to handle the middle part tensile forces. The construction on the pools began after the last of the roof beams were lifted. The pools were cast in place to make them as watertight as possible. For watertight pool, the three conditions are as follows. First, the pool tanks prevent water leakage due to crack from the tank walls. Second, the pool tanks prevent water ingress from the high groundwater level and potential river flood. Third is the pool must maintain quiet wave because the Olympic Games in which records are very important. First of all, to make the watered ground condition, they installed a temporary sheet pile wall containing building site and considering a river located next to it. By doing this, the aquatic center's temporarily cut off wall effectively formed three sides of a box linking to a final side formed by the river wall. And then they need to control the water streams at the pool because the fluctuating water waves cause a significant effect to athletes' record. For example, when soil shake occur, the pool tanks fluctuate and divert the water waves to the quiet to wild. So to prevent these fluctuating water waves and ensure stiffness of pool tanks, they installed these tension piles. The tension piles hold the pool tanks for swaying soil. Finally, this tension pile increases pool tanks stiffness. Not only that, all pool tanks had to fully integrate the water supply pipework, light, footrest, floating floors, and deck level transfer channel required to provide an Olympic standard. These are the study plan. So far we did presentation for 6 weeks and today we just told you about exterior construction. These are the members of the team. I, 이준수, did narration. 구대성 did PPT design. 신선우 and 임영규 and 양재영 did research about the exterior construction. And this is end of our presentation. Thank you for listening.